Hey there, welcome back to this AI-3026 Developing AI Agents in Azure course, where this module covers how to orchestrate a multi-agent solution using, again, Semantic Kernel SDK. My name is Peter Ditender. I'm a Microsoft technical trainer here at Microsoft for almost 6 years now. My Azure background has always been architecture and DevOps, but I gradually shifted more to app modernization and, no surprise, AI and Copilot solutions for about 18 months. This module is one of the 5 modules in this course. You can choose to go through all modules or only a few, depending on your needed skills and where you are already in your developing AI agent journey. Now, you might think that this module is a repeat from the other developing AI agents with Semantic Kernel that we covered before. But you will see that there is still a lot to uncover, especially around that multi-agent orchestration aspect. I would say let's get started. Now, the first question we want to answer as part of this module is really, what is actually a multi-agent solution? Now, in short, a multi-agent solution allows your AI agents to start collaborating within the same conversation. So it's basically allowing different agents to communicate with each other, or allowing a conversation to go from one agent to another. Building a loop of AI agents, that's what we're basically doing. So maybe this is where they might start plotting to take over the world. Now, do not get you scared too much. Let's use another more business-typical scenario, like a DevOps monitoring and issue resolution solution, where in step 1, you would have a monitoring agent, which continuously ingests log and metrics, detecting anomalies using natural language processing that we called NLP before, as well as using trigger alerts when issues arise. Next to that, you might have a root cause analysis agent, which then correlates these anomalies from that previous agent with recent system changes, using, for example, machine learning models or other predefined rules to pinpoint the root cause of the problem. And then next to that in our cycle, we have another automated deployment agent. And that agent is now taking over to implement fixes or performing a rollback for problematic changes by interacting with our CI/CD pipelines, and from there executing deployment scripts. To then eventually in step 4, finally having a reporting agent that generates detailed reports summarizing the anomalies, root causes, and resolutions, and then from there notifying stakeholders by, for example, sending an email or using other communication channels. I think this sounds pretty cool, right? Now, one key feature of the Semantic Kernel Agent framework is its support for intelligent multi-agent interactions. Agent collaboration can be achieved using agent group chat, which has some critical components to consider that aren't necessary with single agents or non-agentic Semantic Kernel applications. For multi-turn agents, agent selection is determined by selection strategy. The selection strategy is defined within the framework, either by using a predefined selection strategy or by extending a selection strategy class to define custom selection behavior. As a developer, you can define the selection strategy when you create that agent group chat object. Next to that, we have sequential selection strategy. The sequential selection strategy class offers a predefined selection strategy where the agent turn order is based on the order in which the agents were added into the chat conversation. The option to specify an initial agent is obviously also available. Another one is the kernel function selection strategy class. This class allows you to define your selection strategy by creating a kernel function based on a prompt. And then we also have the selection strategy base class. This base class contains an overridable select agent method where you can define custom logic for selecting the next agent. The return value must be another agent that is already present in the group chat. And then once you decide on your selection strategy, you can assign it to the selection strategy parameter of your agent group chat object. Multi-turn conversations have responses returned asynchronously, so the conversation can develop naturally. However, the agents need to know when to stop a conversation, which is determined by the termination strategy. The termination strategy ensures that conversations or tasks conclude appropriately. This strategy prevents unnecessary messages to the user. It also limits resource usage and overall improves the user experience. Now, if you're wondering why to use a termination strategy, well, there's a couple of different reasons. First of all, it provides efficiency, which means it prevents endless loops or prolonged interactions, basically saving computational resources. It also provides user satisfaction, which means that users receive concise and relevant responses, avoiding frustration from overly long conversations. Next to that, it also provides goal completion. The use of an agent is, in the end, to complete a certain task. By terminating appropriately, it confirms when a task or conversation has achieved its intended purpose. Similar to how the selection strategy is specified, developers can define a termination strategy or use a predefined strategy. Each termination strategy supports a maximum iterations parameter that will end the chat after a maximum number of iterations, which by default is 99. Each termination strategy also requires the agents which should run the strategy, which I think makes sense. Once you've decided on your termination strategy, you can assign it to the termination strategy parameter of that agent group chat object we already referred to before. A key feature of Semantic Kernel Agent Framework is its ability to facilitate interactions across multiple agents. Using agent group chat, developers can create dynamic, multi-agent conversations where different types of agents start collaborating to generate responses. The agent group chat class extends the agent chat framework, providing you with a structured way to manage multi-agent collaboration. It offers built-in mechanisms to control conversation flow, define collaboration strategies, and support single-turn or multi-turn interactions. To create the agent group chat, you can initialize the chat object with a predefined set of agents. I would say it's basically moving from those complex, multi-thousand lines of code application snippets we discussed earlier into a few semantic kernel building blocks, methods, and classes, which could be summarized in these 4 steps listed here. Now, as you already know by now, my personal saying is it always works in a PowerPoint slide. But you also know I like to show you live how to actually build all this. In this demo, you can join me again in creating an application that automatically triages and resolves issues presented in log files of a system. Using Azure AI agents, we will create an incident manager agent as well as a DevOps agent who then nicely start collaborating and in the end fixing all issues. So we got our baseline Azure AI Foundry setup done. I imported some sample code here, assuming that you might follow along using the link in our Learn platform. I did a git clone, and since this is module 5 in the course, I'm inside my subfolder lab files 5 and inside Python because that's the language we're using. Now, if you are just jumping in here, like this is the only module you've been watching so far, you might get a little bit confused where you go like, wait a minute, Peter, we are developers, so what are you doing in the Azure Cloud Shell? Now, I wanted to make this as easy as possible to show you, but also, I would say maybe a little bit platform independent, which means you don't need to use VS Code or Visual Studio, or maybe you're using some other development environment as a Python developer. I wanted to show you that it's all possible from within Cloud Shell as well. So from here, I can actually show you the next part, and that's using a little minimized version of Visual Studio Code from within Cloud Shell. You can trigger this using code dot, and that's opening up a little version of Visual Studio Code. Now, to make sure that our application agent can connect to AI Foundry project, we need to update our connection string, what you see up here, and we also need to define our deployment model. You can find that information in the Azure AI Foundry portal, and that's what you find over here. Don't get confused that it's not the API key, it's not the endpoint, but it's really the full combination of all that, and that's what we call that connection string. Next to that, we have our sample code, and again, this is our little sample application where we're going to create the multi-agents using our DevOps imaginary scenario. Now, I'm going to help you a little bit going through some of the core building blocks inside our sample project code, not explaining all the steps in there, but mainly zooming in on the core language code snippets, I would say, that you need to interact with your AI agent service. Now, to help you a bit with that, I'm going to switch to my local Visual Studio Code because it's just a little bit easier to zoom in, zoom out, and walking you through some of the core code snippets. I'll make it a little bit bigger. And again, you should already have all these steps out of our lab exercise if you're following along. But if you go like, well, I just want to see it in action and I'm not really following along, which obviously is totally fine, I think it's still beneficial to know what actually happens in some of the code snippets. So the first part is loading the necessary libraries for our Python application to interact, to recognize, you could say, Azure identity, where we're going to create a default Azure credential. And then we're going to load a whole bunch of Semantic Kernel agents, agent strategies, chat messaging, using authoring, and the kernel function decorator. All components, building blocks that I explained in the presentation. We have our incident manager. It's just a sample application. We got our DevOps assistant. And then from here, again, I'm not explaining all the sample code we have, but focusing on the components that you need to interact with your agent and literally having your agent up and running in no time. So what we have is our main function over here. And the main function is where actually most of the code to implement our multi-agent solution is available. Next to that, we have our Azure AI agents. That's what you find over here, where we're going to use the Azure credential. We're going to create an incident agent, and we're going to create our Semantic Kernel agent. If you're struggling with recognizing some of these steps, I would recommend you going back to our first Semantic Kernel module, where I'm spending a bit more time on explaining all that. Now, most important here is we have this loop, we have this multi-agent scenario, which means we're going to have a semantic agent for incident manager. We're going to connect to the agent. Next to that, we're going to build up a Semantic Kernel agent for DevOps. And we're also respecting our chat conversations. As part of our sample code, we also process some log files. That's where we have like monitoring metrics in our imaginary DevOps or maybe SRE scenario. Nothing of that is actually agent specific. So where it becomes a little bit more relevant is down here, where we're going to capture the history, like really having that conversational context, not between myself, the user, and the agent, but now actually between the two agents. That's where you're going to balance out your DevOps assistant is waiting for information from the incident manager, Semantic Kernel agent, and basically going back and forth. And then you might also remember that we need some termination. That's where the approval termination strategy class is coming in. What you see up here on screen. And the approval termination strategy class is what we're going to use to implement the logic needed to determine when the conversation should end. And then we got the DevOps plugin and we got the log file plugin. The DevOps plugin is really calling the function to perform some DevOps operations. And then the log file plugin is what we use to recognize and read out some log files. We're almost at the end of our sample code, where the only thing left is starting it. Now, you already know I'm not going to run it from my local Visual Studio Code, but what I'm going to do is grabbing all the code snippets from here and then pasting them in my VS Code inside my Cloud Shell. I'm going to save my changes, Control S, and I don't need to be inside my code view anymore, which means I can use Control Q to actually step out. And then the last thing I need is firing off my agent. So I'm going to run Python to trigger my agent. And from here, it's producing some output. So what it's going to do is getting some log files, like looking into my DevOps environment, you could say. And then you're going to see there's a going back and forth communication between the incident manager, the DevOps assistant, back to the incident manager, back to the DevOps assistant, and it continuously loops back and forth. So it's picking up some of my log files, like this is where my environment, my workload is running. And now my incident manager is kicking in. So what it needed to do based on the log file is increasing quota, sending it to the DevOps assistant agent, successfully increasing quota, checking back like, hey, is my workload system healthy? All good, no action needed, giving it a little bit of time, and then it's going back to the incident manager, checking my environment, handing it back to the DevOps assistant, and again going back and forth. I just want to keep this on screen for a couple of minutes to show you that it's actually that continuous loop. There you go. As you can see again, my incident manager kicks in. This time there's a new action to be taken. Redeploy the resource. It's redeploying the resource and then validating back as the incident manager agent, like all healthy, no further actions needed. It's going to look into the next metric and then again triggering some action. To me, this is a really powerful example where we're going to build out this collaboration across different technically standalone agents, but now bringing them all together. I'm going to wrap it up here inside my demo environment, and I'm going to shift back to my presentation for the last couple of words and then closing our module. In this module, you learned how the Semantic Kernel Agent Framework enables developers like yourself to build collaborative AI agents. You learned about agent selection. We talked about multi-agent collaboration, and as discussed, termination strategies to understand how agents interact, how they process input, and how they determine conversation flow. You also learned how selection and termination strategies provide that efficiency and goal completion in agent-driven workflows. By applying these concepts and skills, you can leverage the Semantic Kernel Agent Framework to create dynamic, adaptable AI solutions that truly enhance user interactions and automate complex tasks.